Right. Yeah, but is it okay now? Is it trying to?
Okay, I don't know how the others. So okay, I think it's
In
fine.
principle, I would grab another camera from the other room, but I don't want to delay this much. So.
Okay, go on. Maybe it's just me.
I think if you get a bit close, it will be
Yeah.
better.
I'll get closer and turn down the volume.
Yeah, that could be too.
It's just the background noise, so I guess that if you get closer to the microphone, it would be better.
Is it okay now? Okay, a second.
Not really. So can you talk now?
Can you hear me now? Okay. So I guess it's still too loud, right?
Well, it's still a bit low.
It's still a bit low. For now? Okay. Is it any better?
So maybe we can have a balance between the background noise and the.
Yeah, this is surprising that we didn't have this issue anymore. Okay, so let me know if.
I think the best thing you can do is to be. Probably the best thing you can do is to get pretty close to the microphone and get.
Okay, so let's just start this way. Yeah, so if at any point you don't hear me, just ask questions. So maybe this is the way to compromise. Okay. So as Jacobo said, I'll be talking about uniting low-scale leptogeneses. And when I say leptogeneses, I mean primarily leptogenesis via neutrino oscillations and resonant leptogenesis. And this is based on recent collaboration with Juraj and Nina Gmyasov. So let me start, and here is some outline of the talk. So we'll start, of course, with some introduction, have a brief overview of the neutrino masses and how they're generated.
Sorry, I'm sorry, but your slides are not seen, actually.
I don't see the slides either.
No.
Well,
yes,
I can see the slides.
They are seen.
They are seen, yes.
Okay, thanks.
I don't see them then.
Okay, so the slides are not seen or are seen? How many?
So we are seeing them, I think. So it might be
we can see them.
problem of some people.
Maybe if you click in there are two windows. One of with the camera, typically is the small one on the corner, and the other one with the slides. So if you click on the slides, you see the slides, and you click on the camera, you see the face of Jura. Go on, we can see the slide.
Okay, I'll continue. Yeah, sorry, sorry for the technical difficulties. Okay, so yeah, I'll overview these two low-scale leptogenesis mechanisms, resonant leptogenesis and leptogenesis through neutrino oscillations, and then finally we'll go through see how these two mechanisms combine and what does this mean for the parameter space of low-scale leptogenesis. So let's start with the introduction. As you all well know, disarmal is one of the best theories we've ever had, but it still has some small issues. And here we're trying to address two of these issues. One of them is the existence of the baryon asymmetry of the universe, which was confirmed by cosmological observations. And the other one is the existence of these surprisingly small neutrino masses. And what we're trying to do is we're trying to solve both of these problems at the same time. So if we're trying to solve a problem of, that has to go beyond the standard model, one logical place to look for inspiration is the standard model itself. And if you look at all the standard model fermions, we see that all of them appear in left-handed and right-handed chiral partners, except for the neutrinos. So from the neutrinos, we've only seen the left-hand neutrinos so far. And it's an interesting question to see what would happen if we also added right-hand neutrinos to the picture. And this is often referred to as the neutrino minimal standard model. Is the standard model would have neutrinos and nothing else. In this case, we'll consider the special case where we only add 2 heavy neutrinos, just because of simplicity and also because we may want to keep the third one for other purposes. And it turns out that both of these problems can be solved. The baryon of the symmetry of the universe is can be generated through a mechanism called leptogenesis, and the small neutrino masses can be explained through the so-called seesaw mechanism. So let's see how these light neutrino masses are generated. So the first observation that we have to make when we look at neutrino masses that are really surprisingly small. They're the existing experimental bonds that tell us that they're smaller than electron volt. And the interesting thing is that so we're trying to understand why this mass is so low. And if we assume that they are even partially Dirac particles, that they have any component of Dirac masses, this would immediately implies that we need to have right-hand neutrinos in the picture. So this is one way to do this. But the thing is that if we do this, then these Dirac masses are going to be much smaller than any of the other Dirac masses in the standard model. However, these right-hand neutrinos, which we've added to the pictures, are also a special kind of particles, because unlike the other particles of the standard model, they don't have any other gauge interactions. So they are truly standard model gauge singlets, which gives them an interesting property, and that's that they can be their own antiparticles, which means that they can have a Majorana mass term. And the Majorana mass term basically couples the right-hand neutrino to itself. And if we take this totalitarian maxim that everything not forbidden is compulsory, then in principle we have to add this Majorana mass term if we had right-hand neutrinos. And the interesting thing is that we get that the mass sector of the masses of the neutrino sector are going to be quite interesting, and they're going to be described by this mass matrix here. And to find out what the physical states of the theory are, we actually need to diagonalize this mass matrix that's composed of Dirac masses that couple the left-hand and the right-hand neutrinos, and the Majorana masses which couple the right-hand neutrinos to themselves. Now, because of this transpose here, you can see that this is actually not just a 2x2 matrix, but it's actually a block matrix. So these are, so in principle, in our case, this is a 2x3 matrix, and this is a 2x2 matrix if we have 2 right-hand neutrinos. Okay, so the thing to do now is to diagonalize this mass matrix and find out what the physical states are. And what we find is that we get 2 sets of mass eigenstates. We get the heavy states, which are of the order of this Majorana mass, but we also get a set of light neutrino eigenstates. And if we approximately diagonalize the previous mass matrix, this is the EPFL formula that gives us the size of the light neutrino masses. And the nice feature here is that it's proportional to the Dirac mass squared, but it's inversely proportional to the Majorana masses. Which means that if the Majorana masses are big, the light neutrino masses are immediately going to be small. So the heavy Majorana particles give us light active neutrinos. And the thing that we should note here is that if we want to have the observed light neutrino masses, these Dirac masses and Majorana masses are somehow free parameters, but they're also related for the seesaw formula. And we can try to estimate what the size of these masses would be. So if we assume that the Dirac masses are of the order of 1 GeV, which would be quite large, then the Majorana masses would have to be around 10 to the 10 GeV. And this would be quite sad because we couldn't hope to see this in experiments anytime soon. However, if we assume that these Dirac masses are something smaller, and they're closer to the masses of the other leptons in the star model, for example, the electron, around 10 to the minus 6 GeV, then we turn out with the Majorana mass of just 1 GeV. And this looks quite interesting because, well, 1 GeV particles, we can really hope to produce them at future experiments. So how would we produce these Majorana particles? If I said that they don't have any interactions, well, that's the second catch of the seesaw mechanism, that when we diagonalize this mass matrix, and the heavy neutrinos also start to interact with the rest of the standard model. However, their interactions are going to be suppressed by this mixing angle U, which means that this suppression is going to be different for each one of the heavy neutrino flavors, and it depends on to which of the active leptons it couples. Which means that, and if we want to calculate the process is going to be proportional to the square of this mixing angle, and we can express this again by the Dirac masses we had before and the Majorana masses, and this mixing angle is proportional to the Dirac mass, but inversely proportional to the Majorana mass. And as I said before, we have these two indices that stand for the heavy and the light neutrino flavors. Yes, and if we want to have an overall idea how suppressed these interactions are, we can sum overall of these flavors to get what I'll call in the rest of the talk the total mixing angle. And the nice thing is that this total mixing angle can be constrained. So if we look in this this mixing angle tells us how strongly these heavy neutrinos couple, and if we look at their masses, we have this mass mixing plane, which is typically presented in experiments. In experimental searches, we see that there is some lower bound on the total mixing angle coming from the seesaw mechanism itself. There's also a lower bound coming from the Big Bang nucleus synthesis constraints. This is simply coming from the fact that if these heavy neutrinos live for too long, they will interfere with the standard BBM. And of course, there's a number of constraints from past experimental searches in this gray shaded region above. And the reason why this GV region is especially interesting is because there's really a large number of existing and near future experiments that will probe this region in more and more detail. So we might hope to see something in the near future. So this is why we also want to study leptogenesis. We want to see does leptogenesis, or does the existing baryon asymmetry universe predict any of the properties of the neutrinos. So let's slowly see what the conditions to successfully generate the baryon asymmetry universe are. So this was discovered already a long time ago by Sakharov, and namely we have three Sakharov conditions. The first of them is baryon number violation, the second one is CNC violation, and the third one is a significant deviation from thermal equilibrium. And although all of these three are satisfied in the standard model, they're not necessarily satisfied vis-a-vis the plan. So the baryon number violation is immediately satisfied for the so-called Fowler processes, which are non-contributive processes, which allow us to change a lepton symmetry for a baryon symmetry and vice versa. And these processes exist in the standard model for temperatures above 130 GeV. Their CNCP violation in the standard model we have CNCP violation in the quark sector, but this CNCP violation are quite small. And finally, we need the deviation from thermal equilibrium, which is again too small in the standard model because the phase transition is of second order, so we really have a crossover, and this transition is quite slow. It is not strong enough to cause significant deviation from thermal equilibrium. However, if we add heavy neutrinos to the picture, all three of these conditions can be simultaneously satisfied. and we can get CNCP violation in this case in oscillations of these heavy neutrinos, which is schematically shown by this Feynman diagram here. So if we have a heavy neutrino, then we calculate higher corrections, we see that there is going to be an asymmetry for example, in the decay of this heavy neutrino. And the other interesting thing is that we have a significant deviation from thermal equilibrium. And there are going to be 2 points in the history of the universe when there is a significant deviation from thermal equilibrium. One of them is while the heavy neutrinos are being produced, because here we assume that we start with vanishing this condition for the heavy neutrinos. So in the orange line here, you can see the equilibrium distribution for the heavy neutrinos, and here is the actual distribution if we start with the vanishing initial abundance. And while these heavy neutrinos are being produced in the early universe, they're freezing in, we're going to have this whole green area that signifies the deviation from equilibrium. However, once these neutrinos become heavier, then the temperature, since the universe is cooling down, the temperature will drop. And once the temperature drops below the heavy neutrino masses, these heavy neutrinos start to freeze out. And this freeze out will cause another deviation from equilibrium, which we'll call freeze out, and it's signaled here in the red color. And this basically gives us 2 opportunities to generate the baryon asymmetry of units. So maybe let me just quickly overview what the existing mechanisms for leptogenesis are on the market. So for different masses, people consider many different mechanisms. So here I'll point out a few of the more important ones. For very large masses, leptogenesis is typically generated by thermal leptogenesis, and this also satisfies the so-called Davidson-Navarro bound. And this requires, this works even if the heavy neutrinos are hierarchical. So if the masses are not close to each other, so if M1 is much smaller than M2 and M3, then the neutrino masses have to be about 10 to the 19. However, there are 2 famous loopholes to this Davidson-Navarro bound, and that's resonant leptogenesis, which works when the heavy neutrino masses are around the TeV scale. It's shown here in orange color. And there's also leptogenesis via right-hand neutrino oscillations, which typically assumed very light heavy neutrinos around the GeV scale. And for some reason, there was also it wasn't so clear what's happening here in between these 2 mechanisms. Is this part of the parameter space connected or not? And this is really what we're going to consider in this talk and what we consider in the paper, and see how do these 2 mechanisms overlap, do they overlap, and what's the connection between them. So let me quickly remind you, I'm sure many of you are familiar with this, of how thermal leptogenesis works. Yes, Jacobo?
Sorry, Juraj. The thing is that we cannot hear you very well. I don't know if this might get better if you use some headphones or something, or maybe if you have another microphone.
But let me just get my headphones. Okay.
No, it's still the same.
Okay, so
now we can hear. So it's the same. I don't know. Or maybe the other option, if you don't have another microphone, would be maybe to really get super close to the microphone.
maybe in principle I can probably connect to this with my phone as an account, right?
Sorry?
Maybe I can connect with my phone and this could work.
Well, I don't know how
Yeah,
do
you can try, but then you would have to switch off the microphone on the computer, presumably.
Well, you can. No, I mean he can use the slides on the laptop and maybe the microphone on the phone. Sorry for this interruption, but I think it was a little bit annoying, the background noise.
Hi, can you hear me now?
Oh, this is much better.
Okay, the only issue is that I hear myself as well. But yeah, let me
No,
try
but
to
you
see
can
this.
switch off the sound in the computer.
Yeah. Okay. I think this should work now.
Okay, thanks a lot, Juraj.
Yeah, so sorry really about this interruption. Okay, so where was I? I was reviewing thermal leptogenesis, right? So in thermal leptogenesis, the baryon asymmetry is mainly produced in the decays of the right-hand neutrinos. And the fact is that as the universe expands and cools down to temperatures below the mass of the heavy neutrinos, the heavy neutrinos become non-relativistic and begin to decay. And the baryon asymmetry, or the lepton asymmetries, are then governed by this simple differential equation, which tells us what the number of, how the abundance of lepton asymmetry changes as a function of time. And what we have here is the source of the deviation from equilibrium. So it's proportion is the source of the lepton asymmetry. And this is proportional to the deviation from equilibrium of the heavy neutrinos. It's proportional to their interaction rate and divided by the Hubble rate. And of course, we have this key quantity, which I'll call the decay symmetry, which tells us what's the likelihood, what's the ratio of decays into leptons and anti-leptons. So, and it's defined by this fraction here. So that's one thing. And the other thing is that we have also this washout term, W, which drives the lepton asymmetries back to equilibrium. Okay. And the whole catch in this mechanism is that this has to the freeze out of this Fowler processes, which drive the baryon and lepton numbers to be equal, happens after the freeze out of the right-hand neutrinos. This is going to be one of the main differences between thermal leptogenesis and leptogenesis by neutrino oscillations. So if we have resonant leptogenesis, how do we actually calculate this decay asymmetry I mentioned before? So if the neutrinos are hierarchical, there is this famous Davis-Nabarro bound, which tells us that the decay asymmetry has to be smaller than this value. However, if we carefully look at these diagrams, these three diagrams contributing to the decay rate of the heavy neutrinos, and we carefully look especially at this wave function diagram, we can see that it becomes enhanced when the two masses are quite close to each other. Right? So if we just look at this contribution from the last diagram, interfering with the first one, we see that there is this denominator which has a difference of the masses squared. And when we set the masses to be equal, this term is going to basically explode. And this has been known for a long time. So already in 1970s, proposed in the context of baryogenesis. And then there has been a lot of research on this in the context of leptogenesis from the 90s until these days, until today. And this enhancement that happens when the masses are close to each other is what's typically known as resonant leptogenesis. And as I said before, if we take these masses to be exactly equal, we run into some conceptual problems, because then it appears that this decay asymmetry would be exactly infinite. And this divergence is really not a physical effect. This is unphysical, and it needs to be regulated. And one way to regulate it is, so it's regulated by some regulator here, and we want to find out what this is. And the reason why this breaks down is that if we is that we used perturbation theory to calculate this decay asymmetry, which means that we summed up. If we use perturbation theory, then we need to sum up all of these diagrams, because in the resonant regime, they would all contribute almost at the same order, exactly because they all come with this resonant enhancement. However, there's another way to solve this, and that's to go beyond the S-matrix paradigm. And the reason why we really have to do this is because these right-hand neutrinos are unstable particles. And the asymptotic states we would have in the S-matrices simply don't exist for unstable particles. So another way of describing this same process is by using density matrix equations. So if we use density matrix equations, instead of having a number density for the heavy neutrinos, we instead have a density matrix for the heavy neutrino number densities, where you have the diagonals describe the number of particles that we're used to, and these off-diagonals give us some correlations between the two heavy neutrino species. And this is typically described by this type of density matrix equation, often known as Neumann equation. And it's important to note is this equation can be derived from first principles. And we have two important terms here. We have this effective Hamiltonian, which describes the oscillations of the heavy neutrinos, and we have this production rate gamma, which describes how the heavy neutrinos are being produced. So this effective Hamiltonian is proportional to the masses of the heavy neutrinos plus the thermal masses that they have, and the production rate is going to be proportional to their interaction rate. So it's mostly the Yukawa coupling squared times the temperature. And once we calculate density matrix, we plug it into the equations for the active leptons. And then here we have some source term that's a function of this density matrix we calculate from the equation above. And also we have some washout term which describes how the lepton symmetry is being washed out or deleted. And this is one way to calculate things in resonant leptogenesis, and it's been quite useful and efficient. So let me quickly summarize the main things we need to remember about resonant leptogenesis. The first one is that it allows heavy neutrinos to be below 10 to the 9 GeV. There are some conceptual problems if these masses are exactly degenerate, but we can resolve these issues if we use non-perturbative methods. And if we do this, we effectively describe resonant leptogenesis via some oscillation equation for right-hand neutrinos. However, there are also some small issues here, and as the existing studies typically assumed non-relativistic heavy neutrinos and neglected the relativistic effects. And the other important thing is that the non-thermal initial conditions would still require solving the full density matrix equations we showed before. And perhaps one of the most important things is that if we want the heavy neutrinos to decay, this would require the heavy neutrino masses to be above the temperature if we use a naive approximation. So it's not really clear what happens with this regime if we go to masses lower than 130 GeV. So at the same time, there was another mechanism for really light heavy neutrinos, and that's leptogenesis through neutrino oscillations. And unlike the previous mechanisms, which worked mainly through freeze-out, this one works mainly during the freeze-in. So while the heavy neutrinos are freezing in, if their masses are light enough and if their interaction are slow enough, this phallons can freeze out, so we can be completely out of equilibrium and generate some deviation from generate some lepton asymmetry. And this is a flowchart diagram that describes this process. So we start with a standard model thermal bath. There are no heavy neutrinos around, and we start producing them via interaction with a standard model. And we produce them in some interaction states, and these interaction states are typically CP even, and then they start to oscillate, and via these oscillations we generate CP odd correlations. And these CP odd correlations can act as a source for standard model lepton number, and this allows us to generate some lepton flavors. And in a typical low-scale regime, this would be an symmetry in each of the individual lepton flavors. So, and then we can convert this individual lepton asymmetry to a baryon number asymmetry once these lepton asymmetries are violated by the washout process. And here we have the same thing described as a function of time. So on this x-axis we have time, and here we see how the heavy neutrinos are slowly equilibrating. While they're equilibrating, they start to oscillate, and these oscillations become faster and faster. And during these first few oscillations, we generate lepton asymmetries in each one of the 3 lepton flavors. But these lepton flavor asymmetries are slightly washed out. And for this washout, we generate a total lepton asymmetry, which then corresponds to the baryon asymmetry of the universe. And the whole process stops when we reach the electroweak temperature, or the temperature when this Falaron frees out, which is around 130 GeV. Okay. Yes, and so there are several important differences compared to resonant leptogenesis. Here, the whole process depends on the initial conditions, so all of the baryon asymmetry is generated during the equilibration of the heavy neutrinos. The other important factor is that it's very important to distinguish between the helicities of the right-hand neutrinos, because this helicity also carries an approximately conserved lepton number, and if we neglect this, the helicities, we can get quite different results from compared to when we include them. And finally, one of the most important things is that the decay rate for the decay of the heavy neutrino equilibrium distribution can typically be neglected, because the time dependence because the heavy neutrinos are highly relativistic, so the time dependence here is going to be close to 0. So how do we actually describe this process in practice? We have some complicated system of kinetic equations, which are, if we look at them, they look quite similar to the equations we have for resonant leptogenesis, but there is a slight difference, and that's that we have twice as many degrees of freedom, because we also include the helicities of the heavy neutrinos, so each heavy neutrino can appear twice, right? So we have equations for rho n and rho n bar. And one of the final points that's was typically used in equations is to neglect the derivative of this time equilibrium distribution here, which is crucial for resonant leptogenesis, or any type of thermal leptogenesis in the first place. And one of the most complicated things about low-scale leptogenesis is that these rates that enter this computation, if we go back here, these matrices gamma, it's quite complicated to compute these rates correctly. So, because unlike in resonant leptogenesis, the main contribution to the rates is coming from the processes of order of the temperature. So we need to take many of these processes into account to get an accurate dependence, an accurate number for these production rates. And there are typically two types of rates. You have the so-called Fermion number conserving rates, which are just proportional to the Yukawa coupling squared times the temperature times some factor. And this can be of order of the Hubble rate quite often. And there's also something we call the Fermion number violating rates, which are going to be much smaller because they're proportional to the Yukawa coupling squared, but are suppressed by the masses of the heavy neutrinos, which can be quite small in the GeV range. And these rates can be quite small, unless until we look at larger and larger masses. So if mass becomes comparable to temperature, these two rates become of similar size. And we try to take all of these factors into account when studying, in our study of the parameter space of leptogenesis. So let me quickly review what's the existing status before, what was the existing state for leptogenesis via neutrino oscillations. So this is a typical type of parameter scan that was done. There's some lower bound coming from leptogenesis on the mixing angle. There's also some upper bound coming from leptogenesis. The upper bound is coming mainly through the because if the couplings of the heavy neutrinos are too large, they equilibrate too quickly. And there have been several systematic studies of this type in the past years. And what's really nice is that already with these studies, you can see that leptogenesis is within reach of near future experiments. You can do a slightly different study if you use a Bayesian approach. The parameter space looks slightly different, but it's. And of course, this is one of the most up-to-date studies, where both of these Fermi number violating and Fermi number conserving processes were taken into account, and the parameter space remains quite similar. But it's interesting that in many of these studies, they stop around 50 GeV. And there must be a good reason why these studies stop. And so let's see what the main reasons for this are. So, and what lies beyond 50 GeV. So the interesting thing is that there is no, if you look at from the two directions, if you look from resonant leptogenesis coming from above, there's really no established lower bound coming from resonant leptogenesis. There are some early estimates that gave a successful leptogenesis for 200 GeV. There was an updated study in 2016 by Ambi and Teresi that suggested that you could get successful resonant leptogenesis already for 2 GeV. However, these equations were not completely consistent with the results of leptogenesis via heavy neutrino oscillations. There is some discrepancy between these two mechanisms, apparently. And on the other side, if we look at leptogenesis via neutrino oscillations, there are also some issues if we go above the W boson mass, because if above the W boson mass, many new channels open up, and these Fermi number violating and Fermi number conserving processes, they both get quite large equilibration rates. And if we have a very large equilibration rate compared to the Hubble rate, and they're typically 4 to 30 for a mass of 80 GeV, any lepton symmetry that was generated could, in principle, be washed out quite efficiently. And this was the cause for this early estimate by these authors here, that leptogenesis could stop around 80 GeV, and the parameter space of leptogenesis via neutrino oscillation could, in principle, stop here completely. So this is what motivated us to do this study, to see whether the baryogenesis window basically remains open for masses larger than 80 GeV. Yes?
Sorry, Juraj.
Something? Okay.
So the
Teresi and Hambi.
Could you please switch off
the sound?
Well, I'm asking because thank you. Because otherwise I listen myself. Sorry to interrupt you. So Hambi and Teresi, apparently they showed that this resonant leptogenesis can be done just above the GeV scale, and so why is this inconsistent with the leptogenesis via oscillations? Sorry.
I also have the same question. I mean, Hambi and Teresi didn't consider oscillation as a generator of leptogenesis. I mean, they consider just Higgs decays.
but okay, so the catch is really that the oscillations and these decays of the heavy neutrinos, they're okay. So maybe let me slow down first for a second. So what they did is that they used the typical decay asymmetry you would have in resonant leptogenesis. And the fact is that what maybe I didn't emphasize strongly enough is that if I look at these density matrix equations that you should use for resonant leptogenesis close to the degenerate limit,
sorry,
you
you
can use this to actually.
They use a different expression. I mean, it's not the expression for n decays. Of course, it's a resonant expression, but it's quite different.
But they use an equation of this type, and they have some estimate for the interaction rates here for this gamma n. And their statement is that this gamma n is mainly coming from Higgs decays.
Oh, the expression for epsilon is different.
Yeah, yes, indeed. And what I'm saying is that if you want to have an accurate description of this epsilon, then you have to take into account the density matrix equations that we show here. Because the density matrix equation, you can actually use it to derive this decay symmetry epsilon. And it describes exactly the same physics.
Okay, I say thanks.
Okay, I say thanks.
Okay.
You can consider that as an
approximation.
Of course.
Yes, but it's a question of how valid this the approximation is going to be in this regime. Okay. Okay, so perhaps one of the main differences that we did here is that we used the single set of equations for both types of leptogenesis. So we used a set of equations that are, if we have masses much bigger than the temperature, we completely recover the equations for resonant leptogenesis. If we have masses much lighter than the temperature, we recover leptogenesis via neutrino oscillations. And to somehow separate the two leptogenesis mechanisms, right, resonant leptogenesis and leptogenesis via neutrino oscillations, we try to find out what's the difference. Is the majority of the baryon symmetry generated during freeze-in or during freeze-out? So to do this, we artificially solve the equations for freeze-out, where we say that we start with thermal initial conditions, and the only source of deviation from equilibrium is coming from the decays of the heavy neutrinos when their masses become bigger than the temperature. And the other scenario is that we start with vanishing initial conditions. So we generate the asymmetry during freeze-in, but also we artificially set this derivative of the equilibrium distribution to 0. And this is what I'll call pure freeze-in and freeze-out regimes. But of course, the realistic scenario is actually going to be the sum of both of these. And one of the biggest challenges in all of these calculations is to actually calculate the interaction rates. So we estimated interaction rates. So existing rates exist for masses much lower than the temperature and masses much higher than the temperature. And we combined the two estimates by using a rough extrapolation of the relativistic interaction rate and adding it to the non-relativistic decays. And after that, we performed a comprehensive numerical scan over all the parameters for masses between 0.1 GeV and 10 TeV. And finally, we get. Yes.
Can you go to the previous?
Can you go to the previous slide?
So 1m is much bigger than the temperature. What contributes to the resonance lepton? I mean, n decays or Higgs decays in your calculations?
So it's primarily primarily and decay. They give the main contribution to duration. Does that answer your question?
We cannot hear you very well.
Do you hear me now, or are there still issues with the
Yes, yes.
Okay. So here are the main results of our parameter scan. So as I said, we studied leptogenesis between 0.1 GeV and 10 TeV. And it turns out that this baryogenesis window remains open. So there's no, so the two mechanisms of leptogenesis are completely connected. And what's really nice is that there is a significant overlap between these two mechanisms. So as I said before, we can artificially separate them. So here, this red line shows the border for the freeze-in mechanism, where we turn off the source term, or the source of the deviation from equilibrium for large masses, and this will give us this red region here. And within this red region, we can say that the freeze-in mechanism is a dominant baryogenesis mechanism. Of course, there are parameter points within this region as well where freeze-out dominates, and we also have this area bounded by the blue line, where we say that the freeze-out mechanism dominates. So for these blue points, we start with thermal initial conditions and solve the equations numerically as well. And what's really nice is that we can see that both of these mechanisms have a significant overlap. And an interesting thing is that this freeze-out leptogenesis remains possible even for GeV scale heavy neutrinos, while the freeze-in mechanism spans all the way from GeV scales up to 10 TeV, and it even goes beyond. So this somehow explains why the baryogenesis window remains open. And what's really nice is that this whole region of parameter space will be probed in the near future by experiments. So for example, we have the SHIP experiment, which is a typical example of an intensity frontier experiment. And there is also FCC, and already at existing experiments, I mean, not yet existing, but at high Lumia LHC, we could expect to probe a small part of this parameter space. And one thing I didn't mention is that all of this is for normal hierarchy, so we can also look at the same plot for inverted hierarchy. And one more thing I didn't mention is that these contours here, they actually show us what's the biggest mass splitting possible. Biggest mass splitting between the heavy neutrinos consistent with leptogenesis. And so in these shadings, we have from darker color means bigger mass splitting, and lighter color means smaller mass splitting, and everything below 10 to the minus 6 is shown in the white region. And what's interesting is that this region of large mass splittings mainly coincides with leptogenesis via neutrino oscillations, or via or what we call freeze-in. And the same is true here for inverted hierarchy. And the nice thing is that we can get even bigger mass splittings, so between 10 to the minus 2 and 10 to the minus 1. So to understand this parameter space a little bit better, we can look at the different fixed masses and basically take slices of the parameter space. So what we did here is that we fixed the mass to, for example, here to 10 GeV, and we look at all three of these baryogenesis mechanisms for different values of the mass splitting and different values of this imaginary part of omega, which somehow corresponds to the mixing angle. So if the absolute value of this imaginary part of omega is bigger, this means that also the mixing angle is bigger. So what's interesting here is that we see a really nice complementarity between these two mechanisms. So at the GeV scale, we see that the combination of freeze-in and freeze-out almost completely coincides with the labels are wrong here. Sorry, almost completely coincides with the freeze-in mechanism, and the parameter space for the freeze-out mechanism is given by this small blue region here. As we consider bigger masses, for example 100 GeV, we see a more interesting picture. We see that for very large mixing angles, the main contribution is coming, the main part of parameter space is coming through freeze-in, freeze-out, while if we want to have large mass splittings and somewhat smaller mixing angles, we have to rely on freeze-in. Which also means that this region of large mass splittings is going to be highly sensitive to initial conditions. And the same remains true even if we go to 1 TeV. So here we see an even bigger portion of parameter space that corresponds to freeze out, but also this corresponds to leptogenesis via neutrino oscillation remains, and mainly remains for large mass splittings. And another thing to consider here is the size of the mass splitting and the tuning of the mass splitting. So in these lines, in these green lines here, I represent the mass splitting that's induced by the Higgs wave, but also the mass splitting that's induced by the running of the Yukawa couplings and the masses of the heavy neutrinos from some large scale to the electroweak scale. So here we see that, and what's interesting is that for 1 TeV, this regime mainly all these points below the dashed line are going to be somewhat tuned. So yeah, this brings me to my conclusions. So I hope I convinced you that these resonant leptogenesis and leptogenesis for neutrino oscillations are really just two realizations of the same mechanism. We found two nice features: that freeze-out leptogenesis is already possible for GeV scale heavy neutrinos, and freeze-in leptogenesis remains important already up to the TeV scale and beyond. And we found out, and perhaps one of the most important points here is that leptogenesis remains a viable mechanism of baryogenesis for all heavy neutrino masses above 100 MeV, which means that leptogenesis will be testable at already planned for future experiments. There is significant synergy between high energy and high intensity experiments. So if you look at, and together they will cover a large portion of the low scale leptogenesis parameter space. That would be all. Thank you.
Zura, so
Thanks, Juraj. So
for the questions, can I ask you
for
to
the questions, can I ask you to switch off the sound
whenever someone asks something? Like that. Thank you. And then, okay, thanks. Sorry. So first of all, I would like to apologize you all because of these technical problems. We will make sure that the next seminar we fix this, but we managed to survive somehow. So please, questions. Well, in the meantime, I have a question regarding this separation, because you studied both types of leptogenesis using the density matrix approach, but somehow you separate artificially these two things. And what I'm wondering is, so what happens in the regime for when the mass is close to the temperature? I mean, somehow I would expect both things to have a combination of these two things, no? And I'm not sure if what you are doing is analyzing both cases separately, or do you somehow combine the two things?
Okay, so sorry if I wasn't clear about this. So we do 3 studies, right? We do one study where we include both freeze-in and freeze-out. And this is bordered by the dark blue line here, for example. If this meter space that's they call the Vau limits, this is if you include all the effects, this is what we get. And the whole reason why we try to separate is to get also some intuitive understanding behind this, to understand when one or the other regime would dominate. But when we solve the equations, we fully consistently solve both regimes. And this is why we had to sort of artificially try to separate these regimes. And we did this in this way that we started with terminal initial conditions in one case, in the other case we neglected this derivative of the equilibrium distribution.
Okay.
And this
okay.
Jacobo, can I ask
see
you
now.
a question?
Yeah, Sergey has a question.
You're it's a very nice paper. Now, as you know, we did also studies. They're quite different from yours in the sense that we switched off the oscillating mechanism, and then we find that still one can have successful leptogenesis with freeze in and freeze out mechanisms due to decays. So, I mean, this freeze-in possibility is not entirely related to the oscillation mechanism. I mean, it is possible to have it also in the decay mechanism. And also, the range of masses for which you can have successful leptogenesis without taking into account the oscillation mechanism extends down to 0.1 GV. So, I mean, this is all I can comment at this moment.
So, this was one of the points I tried to illustrate when I was talking about these density matrix equations, is that that if you switch the oscillations off, this is going to be an approximation. Would you agree with this?
Sure.
So, okay, and so we didn't use these approximations at all, right? So we used the full density matrix, and we see the oscillations at all times. And these and writing these density matrix equations is just effectively a resummation of all of these diagrams that enter. So indeed, I think it's very interesting that you get this result already for even without needing to use this resummation. So yeah, I will look at your paper more carefully and see if how we can really map these two pictures together, right? Because I think there are some also relativistic effects that need to be taken into account, as I mentioned.
We don't pretend to have done a very precise calculation. I mean, maybe the uncertainty is factor of 2 or 3, but still, it's very interesting that this freeze-in mechanism is possible even for very low masses. I mean, GeV and smaller, just due to the decays.
Yes.
Okay, I think there is another question. So please, you have to activate your microphone. Well,
Hi.
Okay.
Yes. So my question is that in the resonant leptogenesis calculations, we see that the reaction rate is usually for the right-handed heavy neutrino pair decaying to Higgs and lepton. So in the mass range where it is less than that of the Higgs, was that properly? Like, does that change the scenario? Do you have to recalculate the reaction rate?
Yes. So that's true, right? In the resonant leptogenesis scenario, people typically consider the case of heavy neutrinos into the Higgs and the lepton. And there is, if you treat this naively and just look at the 1 to 2 decay rates, this would lead to some forbidden region where kinematically the heavy neutrino just cannot decay. It just could not decay into Higgs, right?
Right.
But of course, if you take a more careful look at the case, include all the higher order terms, you see that this forbidden region is actually just an artifact of using the tree-level approximation. So as soon as you take into account the thermal corrections, for example, for very low masses, the scattering start to dominate, and you don't need to rely on this 1 to 2 rate almost at all. So you have many processes that enter and that somehow resolve this. And what's even more interesting is that there is this effect called the Landau-Pomeranchuk-Migdal effect that happens at finite temperature, and that tells you how to somehow correctly calculate this 1 to 2 rate. And if you do this, I think this was done in a paper by Bodecker. I think I can't remember the year correctly. I think it was 2013 or maybe earlier.
2012.
And then
2012.
Yes, thank you. And then you have a smooth interpolation from the two regimes, right? So you never really have a separation between decays and.
But I think that what Bodecker showed is that the Higgs decay gets enhanced in the region where the N decay cannot happen.
Right, H going to N and L. Right.
So it's not that I mean the mass of the N doesn't get large thermal corrections. It's the mass of the Higgs that can get very large thermal corrections, and then in the region where the N decays are impossible, it is just the Higgs decay that takes over.
Yes, just as in the Thomas Humbe's 2016 paper, I think.
And also, I think that the scattering processes cannot generate a sufficiently large CP violating asymmetry.
Well, I'm not completely sure. Maybe I need to take a look at this more carefully, but I think that the scattering processes enter the equations in the same way that the Higgs decays do. So if you just calculate these equilibration matrices here, they don't really distinguish between the Higgs decays and the scattering. So both of them enter almost at the same level.
No, but the CP violation asymmetry in the scattering, it's a very high power in the Yukawa couplings, and it's just not sufficient for generating the necessary CP violation.
Sorry, I think this is becoming a little bit technical and it's a little bit late, so you can, if you want to continue discussing offline. But
sure.
Given that we are having some really serious technical problems, there is a very last question, maybe if very fast, and then we close. What's the question? Sorry, go on.
So I have a question. So the calculations which you did it using Boltzmann. You used Boltzmann equations. So how much do you expect the results to change if you say use Schwinger-Keldysh methods, closed time path formalisms to do the calculations instead of Boltzmann equation?
Hi, thank you for this very nice question. I mean, so the thing is that what we did is that we actually used the Schwinger-Dyson equation to derive these Boltzmann equations. So, and I think the major, the biggest correction is not going to come from the Schwinger-Dyson equations, but from actually including the momentum independence of these distributions, which we also neglected. So I would say this is the first step, and then perhaps the second step would really be to solve the Schwinger-Dyson equations completely. Yeah. Oh, would this answer your question?
Yeah, okay, I got the answer. Thank you.
Okay, so I think there is still another question. Even if I try to close this, so it's very. I guess it's super fast. So go on if it's super fast.
Can I ask you a question?
Yes, yes, go on.
Okay. So, hi, Juraj. So, could you please go to your plot where you show the mixing versus mass plot for normal mass ordering? I mean, the parameter space. Yeah, this one, yeah. So, the degree of resonance is much more mild, around 1 GeV, no? So, why is that? Is there any reason? I mean, the deep green region.
So the argument here is that I think it's actually a combination of these of multiple things, right? So one thing is that in this region, it's the main mechanism is really going to be baryogenesis via oscillations, and baryogenesis via oscillations favors larger mass splittings. But it's also not just leptogenesis via oscillations. It's the leptogenesis via oscillations is further enhanced by these fermion number violating processes, which are suppressed by m over t. So here in this 10 GeV or larger region, this suppression is not going to be that big. So it's almost a sweet spot. That's true. Okay.
Okay.
Thank you for the question.
Thank you very much. Thank you, Jura, for this nice talk.
Thank you,
In
Juraj.
spite of all these difficulties, and thank you all for the questions. I'm sorry I stopped you, but the problem is that we have always all this problem with the background noise and so on, and I think it's now a bit late. But thank you all. We will make sure that next time we will not have any problem. I'm sorry, Jura, and
Thank
apologize
you.
to all of you.
Thank you.
See you in the
Thank you
next
very much for hosting.
webinar in a couple of weeks, I hope. Bye.
Yes, thank you all for coming. Bye-bye.